Okay. Good morning, everybody. So it's a place for me to introduce Elena from the Universidad of Cádiz in Spain. I met Elena in the last summer in a nice conference that some of our friends of CaRT, like Ismael González Llero and Dorota Kusiak, organized. And then I met Elena. She was invited speaker in this Encuentro Andaluz. We start to talk because I like her conference, her talk. And then we discovered that we have 2 points in common. It was very, very nice. The first of these is that Elena was visitor in Mexico several times in different universities of Mexico. And in particular, she was advisor of 4 PhD students, Mexican PhD students. The second point is that Elena has family in Oviedo, in Asturias, and I have my family too in this city. So it was very nice that we discovered that we have these 2 points. And now I am very happy because Elena and me will have a 3 points with my 3 favorite country in the world, which is Poland. So thank you very much, Elena, for to be here in our CaRT, and it's your time. Thank you.
Okay, thank you very much, Rita, for this nice presentation. It is true, we have, before knowing each other nearly, we already found some things in common, and this was very nice. I'm going to share my slides now, but I do one thing at a time. Okay, so this is it, and now I want to share I hope you can see my slides now.
Perfectly.
Okay, good. And well, before starting, of course, I want to thank all the organizing committee of the CaRT, in particular Rita, but all the organizing committee. For me, it's a pleasure to have the opportunity of being here today. So I truly thank you for this invitation. Okay, so well, my topic is about combinatorial optimization. This is my expertise area, combinatorial optimization. I'm not so much on graph theory, but a little bit more on things on optimization in general, and sometimes things more with an applied flavor, let's say. And what I would like to share with you is, well, what I think that discrete optimization can do, or how can discrete optimization in general help us deal with combinatorial optimization problems. So I'm going to give a very introductory concept. This talk is, I think, it's going to be very easy to follow. So I will first give a definition of what combinatorial optimization problems are in general, and then I will try to explain what can discrete optimization do, how can it help us in solving combinatorial optimization problems. Okay, so I will raise some questions and give some simple answers, but all the time I'm going to, more than go deep into the results, I'm going to highlight the main points I want to show with some examples. In particular, I'm going to work with 3 examples. So everything is going to go with these 3 examples. As you can see, I saw there are several talks on Roman domination. I said, okay, I also want to say something about Roman domination. Okay, so at the end, I will tell you something about this problem, a simple, very simple version of this. Okay, so, well, please feel free to interrupt me if you have any questions or doubts. Otherwise, I will continue. Okay, so, well, here there is a definition of what the combinatorial optimization is. We can define the problem by a triple consisting of a finite set E, which is what typically is called the base set. And then we have a family of subsets of E which is what we call feasible solutions. Not any subset of E is a feasible solution. Depending on the problem, a feasible solution must satisfy some condition or several conditions. And this is the family of feasible solutions. And then we have optimization. I always have an optimization. I always have a function I want to optimize. And here in this presentation, I'm going to work, I did not put it in the title, I did not put it anywhere, but I'm going to work with linear objective functions, with linear cost functions, okay? What does this mean? We're going to have a cost function on the elements of the base set, this function C. So each element of E is associated with a cost or a profit, can be anything. And then I am assuming that this cost function induces a linear cost on the elements of R, on feasible solutions, in such a way that for any feasible solution, the cost of the feasible solution is just the sum of the individual cost of the elements that are inside this set. Okay, so this is the simplest, let's say, objective function we can think of. It's a linear cost objective function. So when I say combinatorial optimization problem, in fact, I'm thinking of combinatorial optimization problem with linear objective function. And then the combinatorial optimization problem is to find the feasible solution that maximizes this cost function, maximizes or minimizes depending on the problem, but whatever. So this is a general definition of a combinatorial optimization problem. Well, one first observation is that, okay, E is finite, so the set of feasible solutions is going to be finite, but of course, trying to enumerate all feasible solutions is not a viable alternative. So in general, this enumeration policy is not viable. It's not even possible because this set I can be very, very, very large. Okay, so we need to think of other alternatives to deal with this problem. Okay, let me show you with a simple example how we start focusing this. Okay, so even if I told you that enumerating is not feasible, with this example, I'm going to start by enumerating the feasible solution. So this is what we call a knapsack problem. And in the knapsack problem, in this knapsack problem, the base set has 3 elements, 1, 2, 3, the cost function. So element 1 has cost 1, 2 has cost 2, element 3 cost 3. And now the characterization of feasible solutions is the following. I have a knapsack. I have a knapsack with a capacity K. In this example, I am assuming that the capacity is 3. And these objects, if each of these objects has a weight given by the elements of this vector A. So element 1 has a weight of 3 or a volume, element 2 has a weight of 1, and element 3 a weight of 2. And the condition is that I want to put elements in my knapsack in such a way that they fit. I cannot put all the elements together because 3 plus 1, 4 plus 2, 6, that's far too much. My capacity is only 3. Okay, so I want to find a subset of elements that fit in my knapsack, but that maximize the cost. So let's look at this and think that this is a profit. So I want to find which is the subset of elements that is more profitable to me that fit within this knapsack. Okay, so here we can enumerate the feasible solutions. And of course, empty set is a feasible solution, occupies nothing, profit 0. All singletons are also feasible solutions because each individual item fits in the knapsack. That's okay. Item 1 cannot go with item 2 or with item 3 because it exceeds the capacity, but I can combine items 2 and 3. Okay, so just by enumerating here, well, it's easy to identify an optimal solution to this problem. In this case, the optimal solution to this problem is items 2 and 3 with a profit of 5. Good. So here we have an example. Okay, what we are going to do is we are going to try to model this problem as what we call as a mathematical optimization problem, and in particular as an integer linear programming problem. How are we going to do this? What I'm going to do is simply associated with each feasible set, I'm going to consider is incidence vector. Okay, so I define a binary vector. This binary vector has as many components as elements I have in the base set E, and then it's just the incidence vector of set I. Okay, so the components of this vector are 1 or 0, depending on whether or not element E belongs to set I. Good. And then I said, okay, so I can write algebraically my combinatorial optimization problem as the problem of maximizing, and this scalar product now is the, so I need to choose, okay, I am computing the elements that have component 1. So in the vector X, so I am computing the cost of the elements that I am using, okay? So I can say, okay, my combinatorial optimization problem is the problem of maximizing this linear function, which is a scalar product with the X. This is a binary vector with these characteristics. Okay, that's fine, but this is essentially the same as we had before. So what we want to do, first thing we want to do is to characterize feasible solutions, okay, by means of a set of equalities or inequalities. I don't want to enumerate the solutions, but I want to find a characterization of what the feasible solution is by defining a set of qualities or inequalities. And again, I want to do as many things as possible if I can do them linear. In this presentation, everything is going to be linear. Okay, so if we, first thing, why do I want to do this? Okay, why one would like to do this? Okay, well, and the answer is because if we are able to write this, to characterize this by means of equalities and inequalities, then we can use solvers, because in mathematical optimization, there are available, there are tools, there are solvers that are available that we can use to solve this type of problems. Okay, so why? This is the reason. This is the reason. There are tools that we can use to solve this problem. So let's see. In this example, I am again with the knapsack. Okay, so these are the 4 feasible solutions. These are the incident vectors of the 5 feasible solutions that we enumerated before. And here, no inequality yet. So I have just written or drawn in this figure. We have the feasible solutions are the blue points. The feasible solutions are these 5 blue points. 1, 2, 3, 4, 5, each of them. Okay, the red points are the solutions which are not feasible. For instance, this one, it would be 1, 1, 1. This would be like if I put the 3 items, and this one and this one. These one are, as I mentioned before, these are not feasible. Okay, so what we want to do is to characterize the vectors. Okay, can I characterize a vector in such a way that, let's say, okay, this is the incidence vector of a feasible solution if and only if it satisfies whatever inequalities. Okay, well, in this example, if we think a little bit, it's not difficult. This, in general, it's not difficult to do. Of course, it depends on the example, but here you see we have the weights of the items. Okay, so, and this is my capacity. So if I want to activate item 1, I will occupy 3 units of capacity. If I activate item 2, I would use 1 unit of capacity. If I activate item 3, I would consume 2 units of capacity. So in total, this is the total capacity I will consume for the items I am activating. Okay, so if the capacity is 3, this must be smaller than or equal to 3. Easy, simple. Okay, so now I know how I can characterize feasible solutions. This is because these X are binary vectors. Okay, so I add, I don't add. Yes or not, I don't add. So now, if I add this hyperplane, if I add this this cut in the figure, So we can see that the blue points are the points that satisfy this inequality. Good. Okay. So now we have, you see, now we have expressed this combinatorial optimization problem as this is an integer linear problem. Integer linear problem. In fact, this is a particular case because we have binary variables. Okay, so it's a particular case of an integer linear problem. Good. And now I can apply a solver. Now I can apply Gurobi, Simplex, Express, I don't know, whichever solver you want. This can be used already. Already. I want to go further, but this already I can use a solver. Okay. Now, my next question is, okay, but here variables are binary. I would prefer to have continuous variables. Because you see, when I have binary variables, this is not continuous, therefore it's not convex, therefore I cannot derive, I don't have derivatives. From the optimization point of view, you see, this can be done, yes, there are solvers, yes, but I would prefer to have a continuous problem. So can I remove the integrality condition on the decision variable? This is the following question. And again, why? Why do I want to remove this? Why do I want to transform an integer linear problem into a linear problem? Well, because I will get continuity, convexity, but in essence, the answer to this question is because a linear programming problem is solvable in polynomial time, whereas an integer linear problem isn't. Okay, so if I am able to get rid of integrality conditions on the decision variables and change them by continuous conditions, then I will be solving a polynomial problem that can be solved in polynomial. But you see, so here, okay, I'm forgetting now, I'm changing the binary conditions on the variables, I'm changing them by continuous conditions. Okay, so now I say, okay, the x must be greater than or equal to 0, smaller than or equal to 1. What happens? Okay, so this is now the drawing. And of course, what I would like is to know if by doing this, I will get an optimal solution of the original problem. Okay, so what I want to get is a binary solution because my solutions are binary. And unfortunately, this doesn't work in this example because you see, well, it depends on the objective function. But if I do this trick, I may get solutions are going to be vertices of the polyhedron induced by these inequalities, but I may get fractional solutions. Okay, so maybe I am lucky and I get an integer solution, maybe, but likely that I would get a fractional solution. So just like this doesn't work. But so I have another question now. Okay, I was using my original characterizations of the solutions and removing the integrality condition based on this description, this characterization. But maybe I can do it differently. Is there a different linear problem that allows me because in fact what I want is to leave feasible solutions as the vertices of a polyhedron. This is what I want. If I leave the integers, the feasible solutions as the vertices of the polyhedron, then by applying linear programming, I know that my solution is going to be integer. This is what I want. So can I change this to a different formulation in such a way that if I remove integrality conditions, then I am sure that I would get an integer solution? Well, in this example, this works. I have to substitute this single constraint by these two constraints. Here we have x1 plus x3 smaller than or equal to 1 is this hyperplane, and x1 plus x2 smaller than or equal to 1 is the hyperplane in the front. If I am smart enough to realize this, okay, then I will be able to solve this integral programming problem as a linear programming problem. Okay, so the main question here is, okay, this is example with 3 variables, blah, blah, this is very easy. And are you lucky, or can you do this? Okay, so so trying to summarize what I'm trying to do, what am I trying to do? We have the vectors, okay, the super vectors of feasible solutions. Here, these are no longer binary. This is a little bit more general, okay? Now, I want to characterize this by means of a set of linear equalities and inequalities, okay? But I want to go further, and I want to eliminate the integrality conditions. I want to eliminate the integrality conditions, and in such a way that what I get is just the convex hull of the integer solutions. Because if I am able to do this, then I can solve my original problem as a linear programming problem. Okay, and the difficulty is here. This is the difficult part, okay? But what does the theory tell us? Okay, I'm describing you in a verbose way what we want to do. What does the theory tell us? Theory tells us, okay, something. The convex set of a finite number of points, which is what we want to characterize. What we want to characterize is the convex hull of a finite set of points. Okay, this is a polyhedron. Okay, this is a polyhedron. It is known this is a polyhedron. More than this, it is known that this polyhedron can be expressed as a system of linear equations. Okay, so it is known that there exists a matrix A of this dimension and a vector B of this dimension, such that this convex hull can be explained in this way, expressed in this way. So this theorem tells us that if I have a combinatorial optimization problem, integer programming problem, there is always a description of this problem as a linear programming problem. But of course, there must be something somewhere, no? Because this is an NP-hard problem, this is a linear programming problem. Well, of course, the bridge is, the thing is that, of course, finding this representation, this exists, it is known how to do it, how one can do it, but it is NP-hard. It is NP-hard. Okay. So, in the end, polyhedral combinatorics is what tells us, okay, how we can go from the integer programming problem to the linear programming problem. So we focus on trying to find complete, non-redundant descriptions of this polyhedron. As much as we can. Sometimes we can, for some problems, we know a complete description. For some other problems, we just know a partial description. But this is what we try to do. Okay. So I want to go now to a problem. I want to show you an example where this works very nicely, which is a perfect matching problem. Of course, perfect matching problem is a problem which is solvable in polynomial time. But we will see something in the meantime, I hope. So we have a graph, we have a cost objective function, and a perfect matching, as you know, it's a subset of edges such that each vertex is incident with exactly one of the edges that we choose. And the optimization problem is that we want to find a perfect matching of minimum total cost. Okay, so the total cost of the edges that I include in the matching is as small as possible. Okay, so here is our example. Again, a toy example. This is our input graph, and the values on the next to the edges are the cost. And well, here it's easy to see. Well, here we can proceed by enumeration. These are because here it's easy to see we have three matchings. This matching M1 is edge 1, 4, 2, 5, 3, 6. This is one matching. Another matching is this one. We have 1, 2, 5, 6, and 3, 4. And the third matching is the one that it is represented here. Okay, so here we have these three matchings. These are the incidence vectors. Okay, but as I did before, what I want is to characterize, so I want to find a description by means of a set of inequalities that tells me this is a feasible vector if and only if it satisfies a certain set of equalities or inequalities, even if I have to maintain the integrality condition of the variables. But this I want to characterize. I don't want to do this. I want to characterize feasible solutions with a set of equalities or inequalities, even if I have to keep integrality. Then I try to remove integrality later. Okay. So for doing this, now it's a little bit more, well, not that difficult, okay, but we have to define the decision variables, and now the decision variables are associated to what we have to do. We have to choose edges. Now we have to choose edges. So now what I do is I define a decision variable associated with each edge, okay? And this variable is going to take the value 1 if I choose that edge and 0 otherwise. I choose the edge. Now, what qualities or what inequalities or what constraints do I have to put? Here, I have to put one constraint for each vertex, because the definition of a perfect matching tells me that each vertex is incident with exactly one of the edges that I choose. So I have to put a constraint that tells me that among edge 1, 2, 1, 4, 1, 5, I choose exactly 1. I have to put another constraint for vectors 2, for vertex 2, that tells me that among edge 1, 2, 2, 6, and 2, 5, I choose exactly 1, and so on and so forth. One constraint for every vertex. And these are the constraints for every vertex. Okay, well, this is the notation. Maybe it's not the best notation, but I did not want to go too much into the notation. Each edge is represented by a pair, and I am assuming that I is strictly smaller than j. So edge 1, 3. I is smaller than so edge 1, 3, not edge 3, 3, 1. So each edge is represented by a pair ij with I smaller than j. So this constraint, you see, here I'm fixing I. So here I am counting the number of edges incident with I that I choose. I is fixed. So those are the edges. For instance, if I is 3, those are the edges with j smaller than I. So here I would have 1, 3 and 2, 3 if it exists. Okay. And here I would have 3, 4, 3, 5, 3, 6. Okay. So in any case, here, since the variables are binary, here I'm counting the number of edges incident with R. 1, exactly 1. And I have one of these constraints for every vertex. Good. So this is the representation for the example that we have. I don't think we need to go into the detail, but for every vertex, one constraint, and I choose exactly one. Now, next, so I have the representation of the problem as an integer programming problem. Next question, can we eliminate integrality conditions? Answer, no. In this example, if I remove the integrality conditions and I allow that the variables take continuous values, this is exactly the solution that I would get. Let me call the attention that this solution satisfies the constraints, because look, what is the edges that I did not draw is because they take value 0. So I only represented the values, the variables different from 0. And here, for instance, vertex 1, 0.5 plus 0.5, exactly 1. So you see the constraint of vertex 1 is satisfied. Because I have 0.1 plus 0 plus 0.1 equal to 1. And with all, and with all the other vertices, the same. With 2, again, 2 edges at value 1/2, 2 edges at value 1/2. So you see, I cannot remove integrality. Well, I can, but I don't get a feasible solution. I don't get an integer solution. But if we look at this carefully, we can again look here. We have like this 3 vertices, they are connected. But if I look at it, I say, okay, but look, if you put edge 1, 2, then you cannot put edge 2, 5, and you can neither put edge 1, 5. And the same with edge 2, 5. If I put 2, 5, I cannot put neither 1, 5 nor 1, 2. So in fact, among these three edges, I can choose at least one, at most one, at least not, at most one. And here, the same. Here, the same. If I choose this one, I cannot choose any of the other two. Okay, so among these three edges, I can choose at most one. And in this example, you take my word, if we add these constraints, we get an integer solution, So the nice thing for the perfect matching problem is that this can be generalized. If I have a node, a vertex set, which is odd, with an odd number of vertices, the number of edges with the two end nodes incident in S, at least S minus 1 over 2, which is the logic I was describing. And then if we add this to the formulation, it can be proven. I will tell you a little bit more now. But you see, so you see, now we have, for the perfect matching problem, we have the integer programming formulation, the original one with the constraints, the degree constraint for each vertex, and the integrality condition. And now here, we have a formulation where we have no longer integrality conditions, but instead, what we have is these odd constraints. Okay, and now this is a complete non-redundant description of the polyhedron. This can be proven formally. This was proven in the 60s. This was one of the first good polyhedral results in the mid-60s. Okay, what's the difficulty here? The difficulty here is that there are an exponential number of these constraints. Okay, so this cannot also be handled easily because I cannot put initially an exponential number of constraints to this formulation. So this raises another difficulty, and the difficulty is to solve what we call the separation problem. Okay, because what we try to do is to add iteratively these constraints. Okay, so we solve the problem without these constraints. We find the point exactly like I did here. I solve the problem without these constraints, and then I identify one constraint that is not satisfied, and then I add it, and then I resolve. And I do this as many times as I need. Okay, and this is what we call the separation problem. I want to characterize this polyhedron, the convex hull. I have a point. I don't know if it is integer, if it is fractional. I have a point, and I want to know this is like an oracle. I want to see if the point is in the polyhedron. In this example, this point is not in this polyhedron, and if it is not, then I want that this oracle gives me a constraint that is violate inequality, that the point does not satisfy, but it is valid, what we call valid inequality. All the points in the polyhedron satisfy this. And this opens the window to an algorithmic solution framework. It is essentially what I told you before. I remove the integrality conditions. This means that I have removed the integrality conditions. I solve the problem. I get a solution. I solve the separation problem. I identify an inequality. I add it to the problem. I iterate until I find no violated inequality, which would mean that I have solved the problem. Okay? Okay. So this is algorithmic framework to solve combinatorial optimization problems. And I want to finish just with a simple version of Roman domination, which is a problem that we are all very familiar with. And well, this is my version. This version, of course, I did an optimization problem. I am nothing with, if I don't have an optimization problem, I don't know what to do. So I need something to optimize. And here, the version I am optimizing, this can be done much more generally, but I did something where the weights are associated. So I associate weights with the vertices, and I try to find the dominating set of minimum total weight. Okay? So I'm looking for a dominating set. So I am looking for a vertex set that satisfies that for all every vertex that is not in S, there exists an edge connecting. There's a typo here. This is W. This is W. Okay, there exists an edge connecting the vertex here, and you see what the reason for which I wanted to put this here is that in this example, before in the two examples I showed you before, we only had a family of binary variables, a family of variables. But here we need two. Here we need one family of variables to identify the elements of the set S, of the finite dominating set, but I need another family of variables to identify the edges connecting the vertices in S with the vertices outside S. You see, this is the reason for which I chose this, to show you an example like this. Okay, here we have two families of inequalities, and I will not go too much into the detail, but just a little bit, let me tell you a little bit. What does this constraint model? I have a pair, ij. If I is either I is in S, because this variable y is going to take the value 1 if I is in S. So either I is in S or there is an edge incident with I. This is why I put here a sum. I don't know which edge incident with I will exist, but at least one. Because you see in the right-hand side, I have one. So if I is in S, I don't need any edge. I am imposing nothing. If I is not in S, then I impose that in the CaRT set, I activate at least one edge. And these constraints, you see, tell me that these variables are well defined. If I activate xij, it is because I is in set S. If this takes the value 1, yi must be 1. So I must be in S. Instead, j cannot be in S. Because if j is in S, this would be 0. So if this takes the value 1, j cannot be in S. And the other way around. If I is in S and j is not in S, then I activate it. Okay, so you take my word, but this is a valid formulation for this simple version of Roman domination. Okay, so I think it's time to finish. I hope to have conveyed my message, which essentially is that discrete optimization offers a very, very, very suitable framework to deal with combinatorial optimization problems. And this is all for my part. Thank you very much. I really thank you for this invitation. And here you have my email address. If you want to contact me, please do not hesitate. I would be happy to clarify anything. And this is all from my part. Thank you.
Thank you very much, Elena, for this talk. We can see very different mathematics. Thank you very much. So I don't know if somebody has a question here, or sometimes in YouTube we have a little seconds later. So nobody has a question, comment? No, by the moment. I have a question. Okay, Julian say really nice talk. You present this Romanation optimization problem for Roman domination, which
Yes.
we have a talk of Roman domination previously in the week. And,
I know.
yeah, and some of us work a little in this domination. But for example, in the case of Magdalena Lemanska, she's expert on convex domination. I don't know if you have this type of problem for another type of domination, for example, particular to convex or any other?
Yes. The reason for which I chose this convex, sorry, let me share again. The reason for which I chose this was envy, only envy, because I looked at the program and I saw there was a talk or a couple of talks about the Roman domination. And this is why, Rita, I thought, okay, maybe you can say something about Roman domination, because I know that this is a topic that many of you study, address, and this and this. I showed a very simple version of a very easy, because I was trying to make it simple enough so you could follow. But I think that I would not say any. I would say that any domination problem can be modeled with this technique. Okay, so yes, more constraints, more sophisticated constraints, but I think that any version of this problem, it has to be optimization. If I don't have no, but I can characterize a domain. We can characterize nearly any domain. Yes, using this type of this methodology. Yeah, and then if you don't have an objective function, then you just optimize a constant. And then you find feasible point. Okay, so if you just want a feasible solution, okay, you can use a constant as an objective function, and then you will find any feasible solution. So here the difficulty is, there are two difficulties. The first difficulty is finding this set of constraints, even if you need to impose integrality conditions. Okay. And this is, you develop expertise with this, and you can succeed nearly always, I would say. Then the second part is being able of removing the integrality conditions, and to get a polyhedron which has integer vertices. This is a different issue. And for instance, in Rome, normally you cannot do this, because if you can do this in a decent way, you could solve the problem in polynomial time. For instance, in the matching problem, why can we do this? In the matching problem, we can do this because matching problem, perfect matching, is solvable in polynomial time. And then we can characterize, because even if there is an exponential, this I did not tell, but even if you have an exponential number of constraints, what determines the complexity of the problem that you solve is the complexity of the separation. Okay, it doesn't matter if you have an exponential number of constraints. Well, it doesn't matter for determining the complexity. The complexity is based on the complexity of the separation problem, which is an auxiliary subproblem that one has to solve. If this problem can be solved in polynomial time, then the original problem, it can be proven that the original problem can be solved in polynomial. Okay, so in the case of the perfect matching, there is this exponential number of constraints, but they can be separated in polynomial time. So this is coherent with what is known, that matching is solvable in polynomial time. You see, but going back to the Roman domination. Roman domination, this is not solvable in well. Maybe there's a simple version. Maybe there's a special case that can be solved in polynomial time, but in general cannot. So maybe I can characterize several inequalities that improve the original formulation. But I will not get a full description of the polyhedron. But this doesn't mean that I cannot solve it, because there are these solvers that deal with integer programming problems, and some of them are quite efficient also, or can be efficient. I don't know if I am answering to your question.
Yes. I thank you. Yes, we will check again. Very careful your talk, as I told you. It is important, and now we can do it, which is great. We don't have to ask for our memory. We can check in the YouTube, because I think it's interesting for us, for all the dominating people, to think about this.
I truly think that it can be useful for you. Yes, I truly think that it can help you For instance, it can help you rejecting conjectures, this for sure. Proving, it's like, okay, if you try and you always get the same type of result, this will maybe motivate you to prove something, okay? It will support your conjecture. But for rejecting conjectures, for sure. Because if you solve an instance and then you get something that doesn't support your conjecture, then you're done. You see? So it can be a very useful tool. I think, I believe. Well, in fact, as you know, we are working with Orota and with Ismael, and I think they are already convinced that this can be useful for. Yeah.
Okay, super. Thank you very much, Elena. I think
Thanks
that
to you.
Julian, you like to.
Yes, I have another question. I don't know if it is interesting to study like the for the feasible solution sets to study like the convex hull of the polytope, even for certain families that could be interesting, or that is not in general the approach.
Julian, thank you for the question. I mean, the approach is precisely this. The approach is you want to characterize the convex hull of feasible solutions. Now, but we want to do this by means of equalities and inequalities. Okay. I don't know, because maybe one can get a theoretical characterization which is not expressed. It's expressed in terms of necessary and sufficient conditions, but these conditions are not translated into equalities or inequalities. You see? So what we want to do is to do this characterization, to characterize the convex hull. This is precisely what we want, to characterize the convex hull, but not by means of not in any possible way, using equalities and inequalities, in such a way that we have the description of the polyhedron by the inequalities that determine the polyhedron.
Oh, okay, but for example, many people that works with I don't know, polytopes or so study like the flags and the symmetries and so of this. I don't know if perhaps for certain families it would be interesting to study these kind of things.
Well, it could be. No specific example comes now to my mind, but I think it can, depending on the problem, it can be interesting because, for instance, there can be a problem, and then for a special case, maybe one can prove, or for certain objective functions, you can prove that the solutions would be in facets or would have certain characteristics, depending on the special case of the problem, or depending on the objective function, of course, because depending on the objective function, you can go to here or to there or wherever. No? So yes, it can be the case that one can study certain facets of the polyhedron, because they apply to specifically, or they are of interest particularly for certain special cases of a general problem.
Okay, thank you very much.
You're welcome, Julian. Yeah, let me add one thing. In fact, in general, the complete description of the polyhedron is not known, but very often a partial description of the polyhedron is known. So in fact, very often what is known is a family of facets, which describes partially the polyhedron, not the full polyhedron. This is a little bit more aligned with what we are saying, I think.
Yes, thank you very much. It's quite nice.
Well, I don't know if we have any more question or comment. Okay, if not, we say thank you again, Elena. Thank you very much.
Thanks to you. Thank you very much. Thank you.
We will be in contact. And now we will have 3 minutes to start with the talk of Ismael. So thank you. See you in 3 minutes.
Okay. Bye-bye.
Okay.
Okay.